this is case number 3 for the simply supported beam. The case number 3 having a statement of simply supported beam with U.D.L, that is uniformly distributed load over entire span. So first of all, we will draw the figure of simply supported beam with U.D.L over entire span. See this simply supported beam. This simply supported beam having two supports. First is A and second is B. This simply supported beam having span of capital L. So capital L is the span of this simply supported beam, and this capital L is the distance between the supports A and B. Now according to statement, simply supported beam with U.D.L over entire span. So see here, over entire span of this simply supported beam there is a U.D.L acting. So over entire span the U.D.L is acting here. So we will draw the U.D.L over entire span of this simply supported beam, and that span is capital L. So we will write here this U.D.L is W per unit length. So W per unit length is the U.D.L which is acting over entire span of this simply supported beam. Now first step we have to do here. First we have to find out these support reactions. Support reaction at A is Ra and support reaction at B is Rb. So we have to find out these Ra and Rb first. So we will write here to find Ra and Rb. So first we will take here summation f of y. So in summation f of y, we will first write Rb, that will be positive, acting in upward direction. Then U.D.L is acting in a downward direction, but this U.D.L we have to convert it into a force. So we will take here W into L. This is the magnitude of the force by converting this U.D.L into a force. So W into L. This U.D.L is acting over a distance of capital L. So magnitude will be W into L. As this U.D.L will be is acting in a downward direction, so we have to take it as negative here. Next we will take Ra, and as Ra is acting in a upward direction, then that we will take it as positive here. Now by applying condition of equilibrium, summation f of y is equal to 0. So 0 is equal to Rb minus of W into L plus Ra. Now we can write here Ra is equal to W into L. If we shift that in the left side, then it will be plus. Then we will shift Rb on the left side, then it will be minus. So Ra is equal to W into L minus Rb. We will take this as a equation number 1. Next we will take the moment about A. Now see here, if we take the moment about A, then the moment of Ra with respect to A will be 0. Next we will take the moment of Rb here. So moment of Rb will be Rb into perpendicular distance L from A. So moment of Rb will be Rb into L, and as this moment of Rb with respect to A is anti-clockwise, so we will take it as negative here. Next we will take the moment of this U.D.L. So the magnitude of the moment will be, see here, from A we have to take the moment of U.D.L. So magnitude of force will be W into L, Now into perpendicular distance. Now see here, as the UDL is acting from A and the distance over which the UDL is acting, that is capital L. So the perpendicular distance will be L by 2. So this will be the magnitude of the movement of the UDL, that is W into L will be the force, and the perpendicular distance from A, that will be L by 2, and this UDL is having a movement with respect to A is clockwise, as the UDL is acting in a downward direction, so we will take it as positive here. Now by applying condition of equilibrium, the moment about A should be equal to 0. So we will write here 0 is equal to minus of RB into L plus of W into L square divided by 2. If we shift this RB into L on a left side, then it will be plus of RB into L is equal to WL square by 2. This LL will get cancelled here, so we will write here RB is equal to W into L divided by 2. So RB is equal to what? W into L divided by 2. Now we will substitute this RB is equal to W into L divided by 2 in this equation number 1. Now see here, if we substitute this RB is equal to WL by 2 in equation 1, then we will write here RA is equal to W into L minus, what is RB? RB is what? W into L divided by 2. Next we will write here RA is equal to 2W into L minus of W into L divided by 2. Then we will write RA is equal to 2WL minus WL should be equal to WL divided by 2. So RA is equal to W into L divided by 2. So as we are getting here RA and RB, so we will write here RA is equal to WL by 2 and RB is also equal to WL by 2. Next step we have to do here, we have to draw shear force diagram. So for shear force diagram, we have to first do the shear force calculations. So these are the sign convention for shear force. So now we will write here the shear force calculations. So to do the shear force calculations, we will start from our right to left. So on the right side, the first is this point B. So we will write here the shear force just right of B. So shear force at a section just right of B is this section. Now see on the right side, there will be a no force, so it will be 0. Next we will take shear force at a section which is just left of B. See here, this is the section which is just left of B. Now see on the right side, there is only reaction RB is there on the right side of this section, and this reaction RB is acting in upward direction. So right side of a section, if the load is acting in upward direction, then according to sign convention for shear force, that load or that force will be negative. So we will write here minus of RB, then we will write minus of, what is RB? RB is W into L divided by 2. Next we will take point A here or support A. So we will write shear force at a section just right of A. See here, just right of A. This is A point. Just right of A is this section. Now see on the right side. First is load RB, and that is acting in upward direction. So right side of a section, load RB is acting in upward direction. So it will be negative. So it will be minus RB. And next is U.D.L. See this U.D.L, which is acting in a downward direction on a right side of this section. So this U.D.L is acting over a span of capital L. So we will take first the magnitude of force, that will be W into L, and as this U.D.L is acting in a downward direction on the right side of a section, so right side of a section, if the force is acting or a load is acting in downward direction, then the shear force will be positive. So here it will be plus W into L. Now we will write here minus of RB is what? WL divided by 2 plus of W into L. Now we will write here minus of WL minus of WL plus of 2WL. We are multiplying this WL by 2, then minus of WL plus 2WL divided by 2. Now we will write here minus WL plus 2WL is equal to plus of WL divided by 2. So shear force at a section just right of A is plus of WL divided by 2. Next we will take the shear force at a section just left of A. See here, this is the section which is just left of A. See on the right side, first is RB. So we will take here RB. This RB is right side of a section acting in a upward direction, so it will be taken as negative. Next is U.D.L, which is acting over a span of L, so we will take W into L. This U.D.L is acting in a downward direction on the right side of a section, so it will be plus. Next, see this RA. We are taking the shear force at a section just left of A, and then we are seeing on the right side. So first RB, next is U.D.L, then this RA. Right side of a section, this RA is acting in a upward direction, so it will be taken as negative. Now we will write here what is RB? WL by 2 plus of WL, next minus of what is RA? RA is also WL by 2. Next we will write here shear force at a section just left of A. That should be minus of WL by 2 minus of WL by 2 minus of 2WL by 2 plus of this WL. Now this 2 will get cancelled here. So minus of WL plus of WL should be equal to 0. So the shear force at a section just left of A should be equal to 0. So these are the shear force calculations. Now we will draw the shear force diagram. To draw the shear force diagram, first we will draw the baseline here. See, this is the baseline. Then we will write here, this is B point, this is A point. Now we will plot the magnitudes here. So right of B, the shear force is 0, so that will be on the baseline here. Now left of B, the shear force is minus of WL by 2. So as it is negative, so it will be below the baseline here. So we will plot that here, minus of WL by 2. Next, shear force just right of A is plus WL by 2. So we will plot that here, shear force just right of A, WL by 2, so it will be above the baseline as it is positive. So we will plot that here. So it is plus of WL by 2, and next shear force just left of A is equal to 0, so that will be on the baseline here. Now we will join these points here. So we will join left of B and right of A. So left of B and right of A. Left of B is minus of WL by 2 and right of A is plus of WL by 2. So as there is a loading between A and B, so the shear force diagram will be the inclined straight line. Shear force diagram will be the inclined straight line. So this is the inclined straight line we have drawn here. Next we will close this figure here, then we will join this left of A and right of A, left of B and right of B. So as this section is above the baseline, so it will be positive, and this section is below the baseline, so it will be negative. And this is the shear force diagram for this simply supported beam with U.D.L over entire span. Now see here, this is the point here. This point is the point where shear force is suddenly changing its sign from positive to negative or negative to positive. So this point on the shear force diagram will be the point of contra shear. Why? Because at this point the shear force suddenly changing its sign from positive to negative or negative to positive. So this will be the point of contra shear. So at point of contra shear the shear force is 0, but there is a bending moment. So we have to calculate the bending moment at point of contra shear, and because of that we have to know the distance of this point of contra shear from one of these supports. So we will plot this point of contra shear here on this simply supported beam, and we will take the distance from support B, of this point of contra shear, that is X. Now we have to find out this distance of point of contra shear from this support B. So we will write here point of contra shear. At point of contra shear the shear force is equal to 0. So we will take the equation for shear force at point of contra shear. So see here the shear force at point of contra shear. So this is point of contra shear here. See on the right side there is a RB. So RB is acting in an upward direction. So right side of this section RB is acting in an upward direction. So we will taking as negative according to sign convention for shear force. Next, on the right side of this point of contra shear, see this U.D.L which is acting over this distance X, that we have to find out here. So we will write here the magnitude of force, that will be W into X, and as this U.D.L is acting in a downward direction, so right side of a section the U.D.L is acting in a downward direction, so it will be taking as positive here. Now at point of contra shear the shear force is equal to 0. So 0 is equal to minus of what is RB? RB is WL divided by 2 plus of this W into X. Now we will shift this WL by 2 on the left side, so it will be plus of WL by 2 is equal to W into X. So this WW will get cancelled here. So we can write here X is equal to L by 2, and this L by 2 will be the distance of this point of contra shear from the support B. So X is equal to L by 2, and this is from support B. So we will write here X is equal to L by 2, and this is the distance of point of contrast shear from B. Next step we will do, we have to draw the bending moment diagram. So to draw the bending moment diagram, we have to do the bending moment calculations first. So these are the sign convention for bending moment. So we will write here bending moment calculations. So that we will write here as BM calculations. Now see here, in case of simply supported beam, the bending moment at the supports of simply supported beam should be equal to 0 unless and until there is a couple at the support. So as there is a no couple here, so the bending moment at the supports of simply supported beam will be equal to 0. So MA and MB will be equal to 0. Next we have to calculate the bending moment at the point of contrast shear. So see here, this is the point of contrast shear. See on the right side. First we will take the moment of this RB, and moment of this RB should be equal to RB into perpendicular distance from point of contrast shear will be X. So RB into X. Now see here, with respect to point of contrast shear, the moment of RB is anti-clockwise. So right side of this section, if the moment is anti-clockwise, then the bending moment should be positive according to sign convention for bending moment. See here, on the right side of a section, the bending moment will be positive if it is anti-clockwise. Next we have to take the moment of this U.D.L, which is acting over this span of X from this point of contrast shear. See on the right side, the U.D.L is acting on this span of L by 2 on the right side of this point of contrast shear. So we will write here W into X will be the magnitude of force. See here, we have to consider only this portion of this U.D.L on the right side of this point of contrast shear. So W into X will be the force, and as this U.D.L is acting over this span of X from point of contrast shear, and as it is starting from this point of contrast shear, so the perpendicular distance will be X by 2. So this will be the magnitude of the movement of this U.D.L from the point of contrast shear. Now this sign convention, see, with respect to point of contrast shear, the movement of this U.D.L will be clockwise. So on the right side of a section, if the movement is clockwise, then the bending moment is negative. So it will be minus. Next we will write here the bending moment at point of contrast shear will be, what is RB? RB is W into L divided by 2 into, what is X? X is L by 2 minus of, in bracket, W into, what is X? X is L by 2 into, what is X? X is L by 2 divided by 2 here. Next we will do the calculations here. So bending moment at point of contrast shear is equal to W into L into L. So it will be WL square divided by 2 into 2, 4, minus, see here, in next bracket we will write here W into L divided by 2 into this L divided by this 2 into 2 will be 4, and we will complete this bracket here. Next we will write here the bending moment at point of contrast shear should be equal to WL square by 4 minus of W into L, it will be L square, divided by 2 into 4, it will be 8. Now we are taking LCM here. So bending moment at point of contrast shear will be equal to, here we have to multiply and divide this by 2 here. So 2 WL square divided by 4 into 2 will be 8 minus of WL square divided by 8. Then we will write here 2 WL square minus of WL square divided by 8. So 2 WL square divided by WL square will be equal to WL square divided by 8. So this is the bending moment at the point of contrast shear, and that is WL square by 8. So these are the bending moment calculations. Now we will draw the bending moment diagram. To draw the bending moment diagram, first we will draw the baseline here. See, this is the baseline here. Now this is B point, this is A point, and this here we will take here this point of contrast shear. Now we will plot the magnitudes of bending moment here. So at A and at B, the bending moment is equal to 0, so that will be on the baseline. Next, bending moment at point of contrast shear is WL square by 8. So as it is positive, so it will be above the baseline. So approximately we will take it here. So here it is WL square divided by 8, the bending moment at point of contrast shear. Now after plotting the points or the magnitudes of the bending moment here, now we will join these points here. So first we will join the A and the point of contrast shear. See here, bending moment at A is 0, bending moment at point of contrast shear is WL square by 8. As there is a loading between the A and the point of contrast shear, so it will be the parabolic curve here. It will be the parabolic curve between the A and the point of contrast shear. So the bending moment diagram between the point A and the point of contrast shear is the parabolic curve. Next we will join the point of contrast shear and B. So we will join WL square by 8 and 0. So as there is a loading between point of contrast shear and B, so the bending moment diagram will be the parabolic curve. Bending moment diagram will be the parabolic curve here. So we will join these 2 points, that is point of contrast shear and B, with the parabolic curve, and then we will write here this curve between the point of contrast shear and B in bending moment diagram is a parabolic curve, as the whole portion is above the baseline here, as the whole portion is above the baseline. So we will write here the bending moment diagram is positive, and this is the bending moment diagram for the simply supported beam with U.D.L over entire span. So this is the bending moment diagram for the case number 3 for the simply supported beam with U.D.L over entire span, and these are the shear force diagram and bending moment diagram for this case number 3, that is simply supported beam with U.D.L over entire span.